Welcome back, ladies and gentlemen. Vertical circles, last piece of the circular motion unit, and probably kind of one of those weird ones. This one's a little abstract in a way. It's not too bad. So we just finished with the gravitron, or another way to say it is a rotor type of question, and what we're going to be dealing with now is a vertical circle. Put another way, so far, if I grab my handy circle here, every circle we've dealt with has been horizontal. It's been sitting like this. Now we're going to turn the circle like this. Why is this a big deal? Well, it comes down to the diagram. If I make a little space here, the diagram for circular motion that is horizontal always kind of looks the same. Doesn't really matter what's going on or how we're doing it, assuming that we're on Earth, which, you know, pretty much all of you guys are, unless right now one of you happens to have become an astronaut over the course of this break, and or space alien, not ruling that out yet, is that for the most part, the object is going to be like this. It's going to be spun around the center, and it's going to make some kind of a circle like that, right? It's more of an egg than a circle. Let's fix that up. There you go. So it's going to move in a circular path like this. And in this particular case, we can set it up and say, okay, there is a force applied causing the circular motion, and there is a force of gravity pulling down. And it doesn't matter at which place in the circle this object is, gravity's always pulling down the whole time. Now, this completely goes out the window if we start talking about a vertical circle, okay? So we're going to have our object here, and it's going to follow a circular path. But it's going to, let's make a little bit more space here. It's going to go up and down. It's going to be spun vertically. So I start up here, and then I go down like so, and then I'm going to go back up to the top. So at different points in the position of this object, things are going to be a little different. So I'm going to name these A, B, and C, okay? And let's think about what the diagram is going to look like, all right? In this case here, we've got force applied pushing in, and we're going to have the force of gravity going down. Okay, so this looks exactly like the horizontal circle that I just erased. That part's easy. But let's think about A. Gravity always points down. And the force applied follows the string. That looks different. What about C? Well, the force applied follows the string, and force of gravity points down. So at different times, there's a different sum of forces. If I add the forces that are acting on the object in the directions that are important to a circle, right? Like, you know, there could be a force coming this way out of the board. I don't care. I care about the force going this way towards the center. Here, the only thing acting is force applied. Up here, we have force applied, and we have force of gravity. Down here, we have a force applied pointing to the center of the circle, and we have a force of gravity pointing away from the center of the circle. So it becomes negative. Towards is positive, away is negative. So remember when I said that the force centripetal is just the name we give to the sum of forces? Here it is. In different points in this circular path, we have a different amount of force in total, because sometimes gravity helps and sometimes gravity hurts. Or put another way, sometimes gravity is assisting in keeping the object in a circle, and sometimes it is opposing that. So let's do this with some numbers, okay? We've got our diagram already, but let's throw some numbers on this, right? In our notes, it says here, a yo-yo with a mass of 0.25. Okay, so we're going to have a mass of 0.25 kilograms. So a nice small yo-yo. It's spun vertically with a velocity of 4 meters per second. Okay, so velocity is 4 meters per second. And the radius is half a meter. So let's pretty tight circle. So what is the force applied when the string is at different points, A, B, C? Now, obviously, there's another position we could do. We could do like D on the opposite of B. But we're just going to look at A, B, C, because D and B are the same. Also, obviously, there could be something between A and B, but then it gets into angles, and it gets kind of messy, and so we're going to ignore that, okay? So we're just going to keep it simple. So we're just doing A, B, C. So in the case of A, well, let's do B first. B's easy. So in the case of B, well, the force applied is causing the force centripetal, right? So in order for this thing to stay in a circle, it needs a certain force centripetal. There's my numbers. I can start solving this, and I can go, okay, this is going to be mv squared over r. The m in this case is 0.25. 0.25. The v is 4 squared over the r is 0.5. All right, so we get out our trusty calculator. We go 0.25 times 4 squared divided by 0.5, and we're going to get that this is 8. So in order for this thing to stay in a circle with these requirements, I need a force of 8. So guess what the force applied is? It's 8, because it's the only force that's acting on the object. Now, let's go back to A. In the case of A, this is still 8. It has to be 8. If it's not 8, I won't be in this circle. I'll be in a different circle, or I might not be in a circle at all. So this has to be 8. Well, the force applied isn't going to be 8 because 8 equals 8, sure, but 8 plus something doesn't equal 8. What's the force of gravity involved in this whole thing? Gravity's helping. So it's going to be 0.25 times 9.8. So I go, okay, 0.25 times 9.8 equals 2.45. 2.45 plus some number equals 8. Gee, I wonder what the some number is. If only I could find that with some mathematics. Force applied here would have to be 5.55. So what that means is that when you are doing a vertical circle, at the top of the circle as it comes up, you have to pull down with less force in order to keep it moving in that circular path than at the neutral position in the middle. Well, the opposite is going to be true down here. We already know that this is going to be 2.45, but that 2.45 is now opposing the force applied, which means in order for this to work, the force applied has to be bigger. It has to be bigger by 2.45. 10.45 is the force applied down here. And what that means is, in order for this object to stay in the circle when it gets down to the bottom, you have to pull up. You've got to put extra force in. You've got to work a little bit harder. So you get to take a bit of a break at the top of the hill, and at the bottom of the hill, you got to lift a little bit harder in order to get it to go back up. That probably isn't a big surprise, right? So if we expand on this question, right, it says here, if the string is old and can only handle 10 newtons of force, will it break? And the answer is, yeah, totally, because at the bottom of the loop, it's 10.45 force. That's 0.45 force more than the string can take. So the moment that the string breaks, what does the yo-yo do? Why, it flies off at a tangent. It follows the velocity. The velocity is pointed horizontally. At this stage down here, it should be like this. So it'll fly off that way. There you go. That is how a vertical circle works. Now, this one's a pretty simple example. We're going to try a slightly more complicated one. Still in your notes, so you guys can follow along there. Let's take a look. We're going to take a look at a roller coaster. Because, yeah, it turns out that the amusement parks don't just have gravitrons, they also have roller coasters. People like roller coasters. Well, not everybody, I guess, but a lot of people do. So, for this particular roller coaster here, it says that we're going to have a 50-kilogram roller coaster car. And it's going to be moving along the track at 15 meters per second. Pretty fast. And the track has a curvature of 2 meters, so that's the radius. So, here's going to be what the track's going to look like, okay? It's going to go like this. So, we've got 2 basic areas to the track. We've got a hill, and we've got this dip in front of the hill. And both of them are curved. Okay, I see. Even though the track itself is not part of that full circle, overall, this is a circle. So I can put, for example, a circle like this. Here's the center, and here is the 2-meter curvature. Similar over here, I can take this circle and go, okay, it's like this. And here is the 2-meter curvature. Okay, so now we understand, I hope, where the curvature part comes in, the fact these are circles. So we've got our roller coaster car sitting here. We're going to call this one A, and we're going to call this at the top of the track B. Well, in both cases, gravity points down. Here's gravity, Fg, going down, and here is gravity, Fg, going down. Okay, that part's easy. And of course, in this particular case, nothing fancy going on here, no weirdness. So Fg is opposed by Fn. Has to be, because we've got this track pushing up against gravity, trying to pull the car down. Okay, well that's easy. Then we're going to have force applied. Well, the cart is going this way. And of course, force applied is going to be opposed in this case by the force of friction. So overall, this looks like a very conventional question. Nothing fancy here. No unusual nature here. So we've mapped out the forces on the cars. Now what does the next question say here? What force acts in the circular dimension of A and B? AKA, what forces are pointing towards the center or away from the center? Well, I've marked the centers of the circle, and the arrows that point up and down are the only ones I care about in this context. Heck, I can get rid of the other ones. So, up and down, that's all I care about, because that's the only stuff that matters for the purposes of a circle. The forward and backward are important for getting through the ride, but for the circle, it's just the up and down. So, over here at A, what do we see? Well, here, the force centripetal is found by taking the force normal and the force of gravity. Except the force of gravity, of course, is pointing down away from the center of the circle, and the force normal is pointing up towards the center of the circle. That's very convenient. Even more convenient when we take a look at the other question. Because the other one, well, force centripetal equals, in this case, the force of gravity points to the center, and the force normal points away. Madness. They flipped around on us. Now, of course, the reason that works is because this particular circle, we're on the inside of the circle, whereas this particular circle, we're on the outside of the circle. Okay. What is Fn going to be? Fn, we have to find here by calculating our values. So let's take a look here. The force centripetal keeping this object in a circle. Well, we know how to find that, right? The force centripetal in both cases, because they're the same size circle, is going to be mv squared over r. Okay, so that part doesn't change. Both of them have the same force centripetal because these circles are the same. Right? Obviously, we could have had a track where the two circles were different, but in this case, we don't. So m is going to be 50 kilograms in both cases. And it even tells us the velocity, it's 15. And heck, it tells us the curvature, it's 2. Well, this is super simple now, isn't it? So we put it all together and we get 15 squared times 50 divided by 2. So we're going to get that the force centripetal is equal to 5,625. So that's the force centripetal, but what's the force normal? Okay, well, I can't find the force normal by itself, but I can find the force of gravity. And once again, since the cart doesn't change, once I know what gravity is, I can use it easy. So force of gravity is, of course, m times g. M is 50. This is 9.8. You guys know how to do this by now, I hope. I hope you guys have been doing this tons. So you put that together, and what are we going to get? We're going to get, I think it's about 490. Just double check here. 50 times 9.8 equals 490. Okay, so now that we have our numbers, now we just have to make sure to use them properly. Over here, when we set up the question, we get 5625 equals minus 490 Fn. Over here we get 5625 plus 490 Fn. Okay, easy enough to solve. Here, the Fn is going to have to be a bigger number because I'm subtracting from it to make that, and here Fn will be a smaller number. So when we do the math here, I think I've actually worked it out, and we get that A over here, Fn, should be 6115. So this one here should be 6115. And over here, it should be 5135. So what does this mean? Well, think about if you've ever been on a roller coaster. When you're at the top of the hill and you're going over the hill, your stomach rises up into your throat, right? You get this like whoa feeling as you're going up. And then when you come down, it's like you get pushed into the chair. Well, take a look. When you're on the low part of the track, the chair is pushing up against you. You're getting sort of slammed into it. And when you're up on the high point, you're kind of like floating a little bit. So when you go down the hill, you feel heavier because there's more force pushing up against you. It's pretty crazy, right? But unfortunately, there's something even more crazy here. Because if we look at our notes here, if we look at the answers we got, right? We have a positive force normal in B here. Why is that weird? Positive means towards the center of the circle. We're not going towards the center of the circle, are we? We're going away, so it should be negative. But why do we have a positive? Well, positive force normal means the force normal has to be, in this case, down. It's got to be pointing to the center of the circle. Well, that's not possible. What that's actually telling you is that this situation is impossible to do. If you were to try to do this roller coaster track at that speed, you would not be able to unless the force normal, right, the track, were to like reach up and grab onto you and pull you down to it. This track, the car is going to fly off. Oops. So, yeah, what's happening here? Well, the problem is that what we did is we said, here's the information in black, right? 50, 15, and 2. We said this is the situation that we're setting up. 2 is not going to work as a radius to keep the car, the roller coaster car, on this track. Turns out roller coasters, like a lot of things, have a lot of math in them in order to make sure that they're safe for the general public. Without all that extra mathematics, you throw someone on this thing and it's going to go flying off. So, we can now change things. Since we can't have a positive Fn, right? The track isn't going to reach up and grab you and pull you down to it. The best we can have is an Fn that's 0, right? An Fn that isn't pushing up against you at all. Okay, so if we have a 0 Fn instead, right, we're going to change this up. We're going to change the question here. If Fn is 0 at the top of the track, so if we change this number here to be 0, Fg is still 490, what value of V would allow this to work. Right, we're changing it. We're no longer dealing with a 15 meters per second, which is pretty quick. Instead, we're saying, okay, based on what we've just calculated, I'm going to fly off the track at the top of this hill. How much do I have to slow down before I don't do that? So I take this, I'm going to solve it, and when I do, I get a velocity of 4.42 meters per second. So if we're traveling at just shy of 4.5, gravity alone will keep us moving in a circle, and we don't need any other forces involved. This has a weird effect because it means that we feel weightless. Now, usually, when we're in class, I try to demonstrate this particular technique and point by getting someone to do something with their eyes closed. You can try this at home in a way, right? If you get a sibling or a parent to help you out, this will work pretty well. What you do is you take any old object, right, so say this one, and you put it in your hand and you hold there and you can go, okay, this feels, in this case, it's pretty light. So then I could always try a different object. There's not a lot of things kicking around here near me. Nothing heavy. Nothing heavy. So this feels pretty light, right? But the way that we're used to thinking about weight is that we're used to thinking about weight as gravity pulling things down. But here's the thing. The way that we feel weight is the feeling of us pushing up against that thing. And here's how you can demonstrate that. You take even a very heavy thing, you put it in your hand, you close your eyes, and the person who's helping you lifts the object up. So it's still touching your hand, but now you're not supporting the weight. And suddenly, that object will feel a lot lighter. Even though obviously gravity hasn't changed on it, right? Gravity's still pulling it the same, but because someone else is supporting it, the object feels lighter. Fn is what gives us the feeling of weight. Fg is what causes weight. Don't get me wrong. Fg is what causes weight, but Fn is what gives you the feeling of weight. If I don't have to support the object, it doesn't feel like it weighs anything because I'm not doing any work, right? It's just sitting there. It's easy. I could do this all day because someone else is carrying it. So yeah, that's the big trick. If you are dealing with an object, the feeling of weight depends on the contact force pushing up against gravity. If you don't support it, it doesn't feel like it weighs anything. So what this means is that if Fc is equal to just Fg, if gravity alone is keeping the object moving in a circle, it will feel to anybody involved in that situation that there is no weight. The International Space Station is an excellent example of this, right? We'll say there's no gravity in space, right? So everyone's weightless, they float around. And we see that if we look at a video of the International Space Station. One of the videos that I show you guys is of just that very thing. Well, hold on. Earlier, up here, I drew a picture about forces, and I said that the force holding a satellite in orbit is force of gravity. I just said there was no gravity because you're weightless. How can there be no gravity, but gravity is the reason why we're orbiting the Earth? I mean, the moon is pulled to the Earth by gravity, and the moon is really far away. International Space Station is really close. How are they weightless? And the answer is because they are moving at exactly the same speed as gravity. The International Space Station moves around the Earth, being pulled by gravity. And that means that the force centripetal is caused by Fg. Because of that, everyone in the International Space Station is effectively falling together. And they don't feel any weight because nothing pushes against them. Right now, my shirt pulls down because gravity's pulling it. But if my shirt is floating up, it won't feel like it weighs anything because I don't have to support it. If everything around you isn't having to support you, right? Your feet don't have to support your weight on the floor. The chair, you don't have to be supported up by the chair. You don't feel that gravity pulling down on you. And so you feel weightless. Okay, I know that's a little bit weird, but that is kind of it. That is it for vertical circles. You see how to do them. Mathematically, they're very simple. You just have to make sure that you take into account how many different forces are pointing up and down, or put another way, towards the center of the circle and away from the center of the circle. with that, you guys are done circular motion. And next will be work energy and momentum and impulse. So there will be a test, as I said, going up probably tomorrow. I'll see if I can get it done. And then you guys will be able to try that once you're ready. And after that, there is one more test left, and that is going to be on the last 2 units. So at this point, you guys are getting real close to done. A couple people, obviously, they caught some errors from the last video. That was very good. Thank you. I'm glad you guys are finding these videos interesting and somewhat useful. For those who are still looking at them going, wow, they're really long, don't forget, you can always put them on fast forward there, right? You can increase this playback speed times 2. Right? Anyway, I will leave you guys there, and next week I will talking to you guys about work and energy. Cheers.